So we're going to continue our investigation of derivatives using the difference quotient formula by looking for general patterns. When we found the derivative of the square root of x, we used this algebraic identity. And one of the jobs of mathematicians is to notice patterns and exploit them. If you remember, there is a version of the difference quotient formula that looks an awful lot like that. This version of the difference quotient is just the usual slope formula, except that instead of giving the formula a starting point x and a width h, it gives it both the starting and the end point. That's two ways of doing exactly the same thing. In this case, the endpoints are a and b. The reason this is interesting is because it looks so much like that formula above it. In fact, if f of x equals x squared, then the difference quotient looks like this. Remember, a and b are the endpoints now. We plug in some number a and b into the function, we get a squared minus b squared, because that's what our function does. And in the bottom, instead of having h, which is the width of the interval, we've got a minus b, which is also the width of the interval. Now look at how this compares to that algebraic formula. This is just a factorization of a squared minus b squared. A squared minus b squared over a minus b equals a plus b. So this formulation gives us another way to think about the average slope. It says if I picked my interval to be 0.5 to 1, that is a is 0.5 and b is 1, then the average rate of change of the function between those points is just a plus b. 0.5 plus 1, 1.5. We can calculate the same thing using the x plus h version of the difference quotient. It's algebraically all the same. It just gives us a different way to write down the answer. Notice that we can also find the derivative using this. As b gets closer and closer to a plus b starts to look more and more like 2a as b gets closer and closer to a. And so we can write the derivative f prime of a equals 2a. It doesn't matter what variable name I stick in there, so it's more usual to use x. So we get the same answer we got before. The derivative of x squared is 2x. So it should make us happy that we get the same result using two different versions of the difference quotient, but the point is rather bigger than that. This algebraic trick we used to factor a squared minus b squared also works for higher powers. Here's what it looks like for a cubed. And here's a to the fourth. And we could continue that list down as far as we like. In all cases, we have a to some power minus b to the same power equals a minus b times an expression that has a very predictable form. It's worth understanding how this trick actually works. I've put up here the version where n equals 6. A to the 6 minus b to the 6 equals a minus b. All that's very predictable. The part on the end that grows is also predictable. It starts with the next lowest power. If we have a to the 6th here, we're going to get a to the 5th. And it's going to work its way down the powers of a, 4th, 3rd, squared, 1st, and then finally no a's at all, while the b's increase. You see that? We got no b's, b to the 1st, b to the 2nd, b to the 3rd, and so on. So I've written it out as this piece, the long sum, multiplied by the a and the minus b independently, and I wrote them underneath each other. So there's the a times all that, there's the minus b times all that. And this is called a telescoping sum because something really interesting happens. When I multiply the a by this term here, it increases the exponent on a by 1, and I get a to the 5th b. Well, when I multiply this term by b, I also get a to the 5th b, but it's got a minus sign with it. That's why I lined these up vertically like that. That's going to happen with every single one of these terms. All of the ones in the top are going to be positive, all the ones in the bottom are going to be identical and negative. And all that we'll be left with is a times a to the 5th minus b times b to the 5th. And that leaves us with a to the 6th minus b to the 6th. And this works for any exponent. So let's take a look at f of x equals x to the n and see if we can figure out what the derivative is. The n is any number 1, 2, 3, 4, 5, and so on. In those cases, this algebraic formula that we discovered will come to our aid. We can rearrange it slightly. I've just divided both sides by a minus b, and I get exactly the form of the difference quotient on the left. On the right, I haven't written out all of the terms, but there are exactly n of them. All we have to do is figure out what happens to this as b gets closer and closer to a. So that you can visualize this, I've given an example with n equals 4. So in the long part of this expression here, if a is equal to b, this is a cubed, another a cubed, another a cubed, and another a cubed, and there are 1, 2, 3, 4 of them. So this would be 4a cubed. In general, with n of them, they're going to be n a to the n minus 1. You notice the exponent here is 1 less than the exponent here. So if we switch back to x's, we can write the derivative f prime of x as n times x to the power n minus 1. This rule that we discovered is called the power law. And it says if we've got a function that's just x to some power, then its derivative is that power times x to the next smaller power. So some examples are plain old x, we can think of as x to the 1. And the power law would say we take that 1 down, put it in front, and then we reduce the power by 1. So we get 1x to the 0. Anything to the 0 power is just 1. For x squared, we bring the 2 down in front, like that, and reduce the 2 to a 1. X to the third becomes 3x squared, x to the fourth becomes 4x to the third, and so on. As long as we have an integer 1, 2, 3, 4, 5, and so on, the power law tells us how to find the derivative. Here's a problem for you to think about. Try to fill in the blanks in this table. We already did the square root, which we can write as a radical or we can write as a fractional exponent. Using the same methods that we used in this video, see if you can figure out how to find a general formula for all of the fractional powers, 1/3, 1/4, 1/5, and so on.